All right, good afternoon, everybody. We will get started with the third lecture for Intro Robotics. So today we're going to be talking about forward kinematics and odometry, which will also be the topic of tomorrow's lab. A couple of things before we get into the material though. So first off, we're shuffling some of the lab groups around based on your feedback. So some people had folks not show up for their lab group. Other people may have switched sections of lab. So all of that's going to result in some rearrangement. If you've had a problem, as in like you can't get in touch with one of the people from your lab group, or they just didn't contribute anything to your group this time around, please send an email or a private Piazza post. That way we can make sure that you are put in a lab group with folks that will be responsive. And if you were for some reason not able to join lab last time, or have your group get in contact with you, also reach out and let us know, just so that we know that what's going on, and that'll make it a little bit easier for us to figure out where to put everybody. Okay. Then also lab 1 is due tonight. So if you haven't had a chance to really get involved and do lab 1, or you just thought you might skip it, that might be problematic for you moving forward, just because all of our labs build on each other. And so we're going to assume that you have a particular set of skills from this lab, so that we don't have to continually repeat that kind of stuff moving on. And you will run into trouble, especially because the first lab is meant to get you familiar with Weebots and some of the concepts that you're going to need to get your robot to do some complicated stuff later on. So again, if you're running into trouble with anything, please reach out to myself or the course staff via Piazza or an email to all of us. Do I have any questions on anything related to Lab 1 or Weebots or Teams or any of that kind of stuff? Yes, good question in chat. So do you all need to submit, or just one person? So Canvas is set up so that only one person in your group needs to submit. If again, you've had a problem with somebody in your group, then in your lab report, just write a little blurb that says so-and-so were the ones that did this, and we weren't able to get in touch with this other person. That would help us out. But yeah, Canvas is set up so that just one person in each group will submit. You can also, again, if you were in one of these problematic groups, email submit to us. So send your zipped up file with your lab report to myself, Shivendra, and Himanshu, and we will make sure that you get credit for it. Yep, for screenshots, we'd like it if you had screenshots from each teammate's versions of the tutorial worlds. Okay, looks like that'll do it for questions. I guess if something comes up, just feel free to post it in the chat. So to recap, we covered this last time, but we'll go over it again. Our general roadmap, that's the way that we're going to approach this course, is that we're going to spend the first 4 weeks covering some fairly low-level concepts. So the real low-level details of how do I move motors to get what I want, and how do I do the math to get those answers. So today we're dealing with forward kinematics, and next time we're going to deal with inverse kinematics. And once we've done that, we'll have a solid foundation that we can then use to achieve some more intelligent behaviors. So today, forward kinematics is going to be what we need to do in order to figure out where our robot is, right? So given a list of joint values, where is my end effector? Or in the case of our robot that we're using for our labs, given some number of wheel rotations, where did I end up? And so once we do that, we'll move on to inverse kinematics, which is the inverse problem, which is I have a place I want my robot to be. What are the joint values that would get me there? So a very brief recap of locomotion from last week. So we talked a bit about different forms of actuation. And so, right, like locomotion is the ability to move oneself, and manipulation is the ability to move others. And that is why we are interested in both of these things, because if we can get a robot that can manipulate anything, and we can program that robot to be able to move anywhere, we have a universal mobile manipulator, and then we can start automating some really exciting stuff. And then a really important concept that we went over would be degrees of freedom. And in particular, we talked about 2 types, environmental and robot degrees of freedom, so mechanical degrees of freedom. So with respect to environmental degrees of freedom, we said that if we have some kind of rigid body and we want to be able to describe where it is in space, then we need 6 numbers, right? We need an X, Y, and Z position, and we also need the roll, pitch, and yaw of that robot, or that, sorry, of that object. That gives us 3D for position, 3D for orientation, hence a 6-dimensional pose. And most importantly, if we have those 6 numbers, right, like we know everything we need to know about the location of that plane. So if we had some 3D mesh that described that shape, and we had a point on that rigid body, then we can reconstruct the scene from that information. We also talked about how this relates back to robots, right, in particular. So degrees of freedom could also mean the number of controllable degrees of actuation. So these are the mechanical degrees of freedom. And when we talk about robots, we're going to talk about both of these somewhat interchangeably. And so it's important to realize which degrees of freedom we are talking about. So if I'm talking about something in Cartesian space, that's talking about the environment. So if I say that my robot's end effector, so this Canova-Jaco arm over here, has 6 degrees of freedom at its end effector, what I'm talking about there is in Cartesian space, that it can move, say, X, Y, Z, roll, pitch, yaw. Usually, those are not directly controllable, right? Like there's going to be some complicated combination of joint movements, of angle changes that will make it so that my arm moves along, say, that x-axis in Cartesian space, right? And that mapping is not necessarily something that's easy for us to find. But we do have the math that we're going to go over over the next couple of weeks to figure out how to do that. And so mechanical degrees of freedom, these are joint space, so 1 for each motor typically. And we talked about why it was really valuable for robots to have more degrees of freedom than the environment that they are operating in. So for example, if you have 7 degrees of freedom in your robot arm, then you have multiple solutions for particular 6 degree of freedom environmental positions, right? So you have multiple joint configurations that get you to the same XYZ roll, pitch, and yaw. Can somebody recap for us maybe one reason why that's actually something we would care about? As in, like, why is it even beneficial for me to have multiple solutions for a given target position?
Is it easier to solve for those solutions if there's multiple?
It could be. That's certainly one thing we might consider. And easy to solve can take a whole number of different definitions, right? Like, could be from a computation time standpoint. It could also be that, as Daniel said in the chat, and Ian said in the chat, like, one of those options might not work. Maybe one of those options would require one of the joints of the robot to send a link arm through the table. And so sometimes it's going to be more valuable for us to have multiple options because some of them are going to be infeasible some of the time. So exactly right. All right. So again, just this thesaurus at the bottom, when we're talking about Cartesian space or operational space or task space, we're usually talking about the environment. And so it's usually fairly clear from the math which one we're doing, but we also have specific variable names that we're going to use for each of these. We ended this one by asking how many degrees of freedom does a human arm have? And so, or a typical human arm, and we settled on 7. So you have 3 at the wrist, 1 at the elbow, and 3 at the shoulder. And that's why you can hold your hand in a particular position and then move your arm around a little bit. Those are all of your redundant solutions. Okay, so that's it for our recap of last time. So today we're going to talk a bit about forward kinematics. And in particular, we have to go through a whole bunch of stuff on coordinate systems and transforms, which you may have only seen in linear algebra and hoped we would never return to again. But unfortunately, we actually have to make operational use of this stuff. So we'll do a brief recap of some of that. And you'll have a homework assignment that's going to kind of take you through this in a robotics-centric context. And then we will just assume that we have this tool available for us. So when we talk about kinematics, kinematics is the study of motion. And so the things that we care about when we are dealing with kinematics, right, are the position and speeds of the different links or joints of our robot. Right? And so the kinematics of a robot defines how it moves with respect to its other parts and the environment. And when we talk about something like dynamics, what we're talking about are these later order effects, things like acceleration and jerk, so the second and third derivative of position. Just a bit of trivia, does anybody remember what the other derivatives of position past jerk are?
Snap, crackle, pop.
That's right. I've never gotten a good answer for why that was chosen, but they did this. So anyway, the abstractions of increasing complexity that we are going to be at least characterizing here are kinematics, right? So that's the study of motion. Statics, which is the study of forces on stationary objects, and then dynamics, right, which is the study of forces on moving objects. And in this class, we're pretty much only going to be focusing on kinematics. We can do some modeling for statics and dynamics as part of your final project, but that's more the purview of the advanced robotics course, as you'll see that this is plenty complicated as it is. And so what we want to do with all of this mathematical framework is be able to connect the things that we can control, right? So like the motors on our robot with the objective that you want to achieve. So like achieving a particular position or speed. So put simply, forward kinematics is saying, where is this, given that I know the angles that I commanded my robot to. So I have some set of joints, I have some set of positions. You've now all used VBots, so you can see that there is a set position command for each of those motors on our robot. So if I knew what I set them to, I should be able to figure out where my end effector is, especially if I already know what my robot looks like. And so in joint space, we use Q to define our robot configuration. And a robot configuration is just a list of all of the joint positions, right? So all of the angles that my motors are at. So we call that Q sub 1 all the way up to Q subscript n right here. And so forward kinematics is essentially giving me this function. So I put some robot configuration in, and then it's going to give me a position, right? So where's my end effector at the end? In task space, right? So in my environment, I might have some m-dimensional space. We talked about a 6-dimensional space, but we might only care, for example, about like xy coordinate or xyz coordinates. And inverse kinematics is just going to be the inverse of that function that is going to take in a particular position and then return for me what configuration of my robot will get me there. And this is a very important concept. This is something that you will carry with you for the rest of the course. So whenever we talk about forward kinematics, you have the joints and you want to know where your robot's going to be. For inverse kinematics, you have where you want it to be. You just need to figure out what the joints are. And this is the slide where we just kind of codify that into one place. So at this point, before we actually move forward into the new material and go through a bunch of the math stuff, I wanted to run through a quick quiz on Canvas. So if you hop onto the course Canvas, you should be able to scroll down under the modules to find a Lecture 3 quiz. Now, these quizzes are not graded. That's just for a comprehension check on the course staff's part. So there's no need to do well or poorly on it. Just do as best you can from your memory. And that'll give us a sense of where you're at. So we will take a couple of minutes to go and do that. I'll sit here, and I believe there's an 8-minute limit on the quiz, but hopefully you won't need that long. And so we will start back up again in 6 minutes. Okay, so we'll get back into our material. So yes to everybody talking about it in chat. There is a typo on that. What's interesting is that on average, half of the people picked 7 and half of the people picked 9. The correct answer is 8. There are 8 distance sensors, but I will make sure that that gets fixed. We don't grade these anyway. This is just to trying to see if some of the definitions that we're tossing out there are sticking, which ones aren't, because that's going to be the inform what we review later on. So hopefully nothing on there was terribly surprising, and we will just continue on with today's lecture. So if we're going to talk about forward kinematics, and more importantly, where stuff is in the world, we're going to need some formalism around that. Now, most of you have seen most of this stuff before. We're just going to kind of roll through it just to make sure that everybody's on the same page. And so here we have a number of definitions of different tools that we're going to use for rigorously specifying the world that our agent interacts in. So of course, first we have points, right? So points are going to be used to express locations versus vectors, which are going to be used for things like displacement, movements, and forces, right? So this is going to represent maybe a difference between one location and another. Normals are going to be unit length vectors that we use to describe orientations, right? So a normal is going to be orthogonal to a surface. So again, perpendicular, and unit length just means that it is of length 1. So to put all of that together, we need coordinates, right? So that's just the numerical representation of the stuff we're talking about on the top half of this slide. And in order to have coordinates, you need a coordinate system. And so coordinate system is going to be 3 orthonormal vectors of unit length. So that just means that they are all perpendicular to each other and they are all of length 1. The reason why we need them all to be of length 1 is because that's going to give us some nice mathematical properties that we can exploit later on. So again, just moving in with this like standard notation. When we have a point, we're really walking along our axes, right? So just like a vector is going to have some kind of basis, our axes are going to be our basis. So we're going to say that if we have, let's say, an X, a Y, and a Z position, let's see, it looks like my voice is cutting out for some of you. That could be a consequence of the engineering center's wired internet. Well, if it remains a problem, just let me know. Send me a private chat or publicly, either way. I want to make sure that everyone hears this. Hopefully the recording won't be affected by that in case I really start to get too garbled. But either way, what we're talking about here, right, is just a notation for what it means to have a point, right? So a point in a coordinate frame is essentially just a vector with the basis being my coordinate system axes. So the coefficients are going to tell me how far I travel along each of those. So here I can represent this vector v, right, as saying, okay, go C1 steps down basis vector 1, C2 steps down basis vector 2, and C3 steps down basis vector 3. And I can represent that as a matrix multiplication, or in this case, a vector multiplication. So I could put my axes here, and I can put my coefficients here, and these two notations are equivalent, right? Because when I do the multiplication, I get B1C1 plus B2C2 plus B3C3. Okay, so hopefully this isn't new for anybody, but in case it is, that's all right. Just review your linear algebra and you'll find lots of this stuff. So in shorthand, we're going to be writing this out like this. So default orientation for vectors is vertical. So if you see something that is horizontal like that, we are going to put the transpose symbol there to show that it is horizontal. So when we define our coordinate system, what we're looking at is an origin and a set of basis vectors, right? So we're going to have our coordinate axes, but the origin is going to tell us where that actually is. So here we will say our coordinate system S is going to have some point O as its origin and some basis, or set of basis vectors B. So one thing that's interesting about this conversation that I think tends to just fly past and not get scrutinized too much is this notion of a point O, because we're defining a coordinate system. And in order to have a point, we need a coordinate system to situate that point with it. And so we can't actually put the origin somewhere in the coordinate system that we're actively defining, because that would be self-referential and it wouldn't really make any sense for us. And so in most cases, we're only dealing with one coordinate system. And so this origin is just 0, 0, 0, right? There's no external frame of reference that we're using to situate it with it. But if we do have a different coordinate system, then we can use this origin to show where our coordinate system applies in its external frame. Okay, so if I'm expressing a point in a coordinate system, we're going to use this notation. And I agree that this notation is somewhat bizarre, but it is convenient for us to keep track of what we're talking about. So if I have a point P in coordinate system S hat here, then I'm going to put that S hat as a pre-superscript. So anytime we see something that looks like this, I'm saying that this point is in reference frame S, or coordinate system S. And the way that I would write that out is I have my origin, right? So that's some translation. And then how far I'm going to walk down each of my coordinate axes, right? So my basis vectors. And if I wanted to write this, so a point cannot have a rotation. So we would express the rotation through these vectors B, right? So as long as the vectors are orthonormal to each other, it doesn't really matter if it aligns with whatever external coordinate system that we're dealing with. But that's a great question. And so whenever we're talking about points, we're talking about, say, like XYZ coordinates, there's no notion of rotation there. So we have to put that somewhere else. So if we want to make this into vector math, we would write the same thing out this way, right? So these are two equivalent statements, and it's very helpful to familiarize yourself with kind of recognizing that these are the same thing, because it'll help you to kind of conceptualize some of the notation we're using later. So in this case, because I have this origin, right, just as a standalone term, I've added a 1 here on my coordinate system, or set of coefficients for going down these basis vectors. So this is another trick that you can use to combine these kinds of things together, right? So I have B1, C1, B2, C2, B3, C3, and then my origin and a 1. And yes, the C's are the distance down each axis that I'm going to walk. And we'll go through some examples as we talk about things like rotations. Okay, so we've all probably seen coordinate systems before in some form or another. What might be a little bit new are nested coordinate systems. And so if we recall, we were talking about rigid bodies. And so anytime we have a rigid body, that's really convenient for us because we can usually shrink that down into a single point. Now, if we care about rotation, that's going to be a 6-dimensional point, not a 3-dimensional point. But all the same, if we just have one kind of way to talk about an object, we can reduce it to that vector. And so if we have just this coordinate system, we can fully characterize the kinematic state, which is good for us because now that lets us actually run some kind of mathematical modeling on this. And so let's just quickly talk about something that is more complicated than, say, this one rigid plane. We'll call this maybe like a toy plane, so we don't have to deal with the intricacies of that. But let's start talking about this robot in the bottom right. So how do I model that? For the plane, I just need a 6-dimensional vector for XYZ roll pitch yaw because it's just one rigid body. And if we recall our definition of rigid body, that just means if I pick any 2 points on that surface, then no matter what I do throughout the duration of my simulation, the distance between those points won't change and their relative orientation to each other won't change. So how many numbers am I going to need to characterize, say, this robot manipulator? Okay, why do we say 9?
So there's 1, 2, 3, 4, 5 joints, it looks like, and then it can rotate in space. I guess 7.
So this robot is a 7 mechanical degree of freedom robot. And so we could use the joint configurations, but if we're talking about in, say, Cartesian space, right, in the environment, I'm not going to be able to easily model this with just 6 degrees of freedom, right, because it's not a single rigid body, right, because parts of it can move. So going back to that definition of what a rigid body is, if I pick a point on maybe like the end of the hand over here, like somewhere here, and I pick a point down on the base over here, well, those are going to change as I change the joint angles. And so I'm going to, if I want to start modeling this in, say, Cartesian space, I'm going to need to have a more expressive like technique for modeling this. And so when we're talking about a robot, each one of these segments is a link, and the links are connected by joints. And so I'm going to end up with this nested coordinate system where each one of my links here, right, is going to have a joint or at the end of it. And I'm going to need to then express the next link in terms of the previous one's coordinate system, right? So if let's say I'm rotating my wrist, the position of the end effector is going to be conditioned on all of these other things that come before it. And so now I'm going to be looking at this as, well, each one of my links is a rigid body, right? And so I can use that definition to construct a model of my robot. It's just going to be this nested definition because each link further down the line is going to depend on the rotations of all the links before it. In terms of coordinate systems, what that means is that each degree of freedom that I have or point of actuation is going to present me with a new coordinate system that I'm going to be able to use to figure out where stuff is. And it turns out it doesn't actually matter if we're talking about mobile robots or if we're just talking about the manipulator arms, it's all the same. And so here, right, we can see a bunch of different coordinate frames coming from different joints on this robot, this mobile robot here. And so this is something that we're going to have to deal with when we start talking about modeling the epoch, right? We're going to need a coordinate frame for that robot. If we had a manipulator arm like this, then we're going to also have different coordinate systems for each of these subsequent joints down the line. So here's a kinematic model of one of those robot dogs that you might have seen around the engineering center. And so you're going to have a whole bunch of different coordinate systems on here as well. And we're going to need to figure out how to talk about objects from one frame in the context of a different frame. So I'd like to go to this next slide, which shows nested coordinate frames or different coordinate frames as it talks to this palletizing manipulator arm. So here we have a world coordinate frame, and then we have the robot's base coordinate frame. Here we're going to end up with the end effector coordinate frame. Here's the tip of the end effector's coordinate frame. And here's maybe the object that we care about, and that's going to have its own coordinate frame as well. And so we want to be able to have these translations between them, right, and transformations to accommodate for both the XYZ and the rotations. And so that's what we're going to go through a quick overview of now. This, again, hopefully is a bit of a review from linear algebra, but I do know that when I took linear algebra, I internalized approximately none of it, and I've had to reteach it to myself several times. The question is, in chat, why isn't there a new coordinate system at the second joint of this robot? There are. So you can form a coordinate system at each one of these joints. Just for the sort of simplicity of this figure, we didn't put like all of them on here. It's mostly like when you're using a robot arm like this in particular, these are going to be the more important ones for us to deal with. So in order to go from the coordinate frame from the base of the robot here, where the laser pointer is, all the way out to the end effector, we do want to know the transform between those two. It's less likely that we're going to explicitly be dealing with, say, the transform up to this intermediate joint. And the reason for that is that most of the stuff we're going to do is either going to be from the perspective of this base, or much more likely the perspective of this end effector out here. But that's a good question. So we can talk about these high dimensional nested coordinate systems, but that doesn't lend itself terribly well to a PowerPoint. So instead, we're going to start by talking about 2D nested coordinate systems. And this is very convenient because we are using a robot that is maneuvering around on a planar surface. So we don't really have to worry too much about that third coordinate. So we don't really have a Z coordinate that we really have to care about because hopefully, unless you mistakenly click, drag, and add forces to your epoch, it's not flying up into the air. So here, we're going to deal with three different variables. So we have our X, we have our Y, and we're going to have a theta, which is our rotation, because our robot is orientable. And so because of that, we have to know where it is rotated around the axis that's coming out of the plane. So when we're talking about dealing with these nested coordinate systems, we have to be able to work our way from one coordinate system into another one. And so the problem that we're solving at the core of this is, given that we have some coordinate Q, or some point here, Q, and we might have that point in one reference frame, in one coordinate system, we want to figure out, okay, but how would I express this in a different coordinate system? And so again, here's our notation. So we have a point Q, it is in reference frame B. And so here we have the X coordinate of Q and the Y coordinate of Q in coordinate system B. And likewise, here is that coordinate in coordinate system A. And so you can see that we're essentially projecting, right, this point onto the coordinate axes for each of these coordinate systems. And so when we're talking about points in a coordinate system, this might not be the way that you think about it, but this conceptualization helps a lot when we're trying to figure out, how do we go between these kinds of coordinate systems? Like, what does it actually mean to express a point in this stuff? So if we already know Q in terms of B's axes, then, and we want to be able to figure out where Q is in terms of A's axes, we want to figure out how to convert, right? So how do we convert between these coordinate systems, A and B? So what are the two things that we're going to need to know in order to figure out how to move between these coordinate systems?
The angle between them and where point P is at.
Exactly right. So the angle between them, that's our rotation, and the location of point P in frame A, that's going to be the translation. Okay, so let's work on both of those things, right? So first we'll deal with translation, because that will be the more straightforward one. So for translation, we just subtract A from B, right? In this case, we probably have the points of origin for B, because we had to define our coordinate system somehow. And so if we know where the origin of B is in frame A, we've already got that. So that's going to be our translation. But how about rotation? So for each axis, right, in this frame B, we just have to figure out how to map it onto frame A. So we'll start with just one axis in this example, right? So if I have the point 1, 0, right? So that's 1 unit up my x-axis, or my first axis here of B, and 0 units up my other axis of B. Let's say I'm going to end up over here. Then I need to figure out how much that contributes to the x-axis of A and the y-axis of A. And so we can do that by projecting. So here in green, with this dot over here, we have the point that we care about. So we have to find out the amount of the contribution to each of the other axes. So we can work this out through some established equation that you've had to deal with in the warm-up homework. So if we remember that axes are unit length vectors, right, so that they are length 1, and we recall what the dot product formula is. Can somebody throw the dot product formula in chat if you remember it offhand? Okay, so we've got a bunch of answers. So the length of A multiplied by the length of B multiplied by cosine of theta, right? So that is one definition for our dot product. And what does that reduce to if our axes are unit length? So if A and B are coordinate system axes, and we know that they are unit length, then what is the dot product? Just cos theta, exactly. So that's nice. We also know that you can express the dot product this way. So it is the element the sum of the positional elements multiplied together. So We can also think of the dot product though as a projection, right? So like what amount of this vector, right, is aligned with this other one. And so here, if I dot product, say, the x-axis of B with the x-axis of A, then I'm going to figure out how much of that is contributing, right? So like what percentage of this movement is going along this direction. Likewise, if I dot product this x-axis of B with this y-axis of A, then I'll see how much it contributes in that direction. And so with those things, I can define a rotation matrix, right? So a way to map from one to the one coordinate system to the other by looking at these projections. So if I'm looking at this, I'm saying, okay, so this first entry, right, of this x-axis is going to be how much of my x-axis of B contributes to my x-axis of A. And then I want to know how much of this y-axis, right, is contributing to this x-axis of A. So here I've defined basically how to go from a coordinate in system B onto the x-axis of coordinate system A. And then the next one down here, so sorry if, oh, let's see. Let's see if I can make that come back for everyone. Is that better? Okay, great. So we're just projecting, right, our x-axis and y-axis of B onto each x and y-axis of A, right? So we want to figure out how much each of these is contributing to each other axis. If we have three-dimensional coordinate systems, it gets a little bit more messy, right? Because there's a lot more stuff that we have to write down, but the idea is exactly the same. And so here, if we have a three-dimensional coordinate system, then we're going to want to know the same thing, right? So I have an origin for my next coordinate system. I have it expressed in the outer coordinate system A here. And if I want to figure out, say, how do I map from a point that I know in this space to a point that in coordinate system A, I just have to figure out how much to project. So this notation is a rotation matrix from coordinate frame B. So the one that we're going from is on the bottom, and then into coordinate frame A, the one that we're going to on the top. And so just like we talked about our points having this pre-superscript thing, that'll be consistent. So you can look at the top left to figure out where we're ending up. And so if I want to take this coordinate frame B and express it in coordinate frame A, I just have to project them. So I figure out, so let's do just the x-axis for now. So the x-axis in frame B, right? I can dot product that with the x-axis, y-axis, and z-axis in frame A to figure out like how to translate, that movement down that one axis into movements down all three of these ones. And I can repeat that, right, for my y-axis and my z-axis to get a full three-dimensional rotation matrix. So that'll be a 3x3 matrix. Okay.
I mean, if you're doing three dot products for each of the axes, that's just matrix multiplication.
The rotation matrix that we end up with is just exactly. It's a matrix that we're going to use, and we're going to multiply it into points to translate between coordinate systems. And we'll go through a couple of examples in just a few slides. So I'll take this same idea, and I'm just going to advance one slide. So here we just have our coordinate frames or projections rather mapped out. So for x-axis of frame B expressed in frame A, so here's our x-axis of frame B. If I want to express this in coordinate frame A, then I have to figure out how much do I go down each of my three axes in coordinate system A for each unit, say, of moving down xb here. And so that's what this is showing. So I take this xb and I just dot product it into A. I dot product to x, y, and z in frame A. So if I put all that stuff together, I'm going to get this big 3x3 matrix. And that will be my 3D rotation matrix at the end of this. So if you're completely lost, if like none of this makes sense, or if you think this is like very tenuous grip on what's going on, don't worry. We're going to go through a couple examples and then maybe it will click. And if not, feel free to reach out in Piazza or during office hours and we can go over it one more time. But before we go with that, just a quick justification. Why do we care about using these matrices? Well, for us, two big use cases. So rotations and transformations of objects are things that we have to deal with all the time. So rotate the robot in place, move the robot along some kind of vector, and expressing these coordinate system changes is going to be something that we care about quite a bit because we'll probably have the location of an object in the robot's coordinate frame, right? So we're like centered in the middle of the robot. We'll say the robot coordinate frame is origin there, and then the x-axis is pointing out the front of our robot. And so if you have say like a LiDAR sensor on your robot, well, you're going to get that from the perspective of the robot. But in most cases, we also have some external reference frame that we care about. Well, sometimes it's called the inertial reference frame or the world reference frame. So we're going to want to express things like object detections in that non-robot centric frame. And so for that, we need to be able to figure out how to change between these coordinate systems. Okay, so here's our projections in 3D on the top here. Right, so I have my rotation matrix to go from coordinate system B into coordinate system A. And so this is just different ways of writing that out. Here are visual representations of my coordinate systems. So I have three of those here, S, B, and C. And so if I wanted to go from coordinate system C into coordinate system S, right? So if I have a point in C and I want to express it in frame S, what might my rotation matrix look like? You don't have to answer that immediately. We'll walk through it together. And I'm going to put the answer up first. So this is my rotation matrix to go from coordinate frame C into coordinate frame S. And before we look at any kind of math, we can just look at this one and kind of figure out what's going on. So first, the x-axis, right, of my coordinate frame S. How do I map between coordinate frame C and the x-axis of coordinate frame S? Well, we can look at this top row and we can see that, okay, so first we can look at the coordinate system here. So does X contribute at all on my, does CX contribute at all to SX? No, they're completely orthogonal. So it doesn't matter how many times I go up or down this, it's not going to actually change anything in my new reference frame. So that's going to be a 0. How about for Y? Well, yes. So every step that I go up CY, it's taking me down one step on SX. And so that's what this -1 is. Right? That's how I map between these two things. And then likewise, CZ is orthogonal to SX, so there's no contribution there. Right? So no matter how far I move there, it's not going to change my reading from this coordinate axis. Okay, so now if I want to go for, to map to the y-axis of S, right? So this one, right? I can just look at this and I can say, okay, well, it's the negative z-axis of C. And we can work through that, like that same idea. So if we just start projecting, right? So here's 0, we have 0, 0, -1. So we can try to map this. So this is going to be 0, right? Because they are orthogonal to each other, and cosine of 90 degrees is going to be 0. These are going to be 0, right? Because those are orthogonal as well. And then this is going to be pi, right? So we're going to end up with -1. And then lastly, the z-axis of coordinate system S is the x-axis of C, and so we can see that here. So this is what's going on, right, when we're talking about these mappings between coordinate systems. It's really just like, given that I'm walking down these vectors in some kind of combination, I now have to express it in terms of these vectors instead, right? How if I were walking down these ones instead of these ones. So that's what we're working with here. So is it possible to orient every axis of all of the joints in the same direction? So when you're talking about joints, do you mean like on a robot? So if you constructed a robot where all of your joints were, say, aligned with each other. So they had completely parallel axes. And you can think of this as maybe a robot that can't rotate in place, but maybe it has a bunch of, so maybe it has like a bunch of links and they all just bend the arm along, say, one axis. You could do that, sure, absolutely. The question is, what are you trying to accomplish with that kind of system? And so generally speaking, robot designers are careful to make sure that their joint axes aren't always aligned, like fully aligned with each other. So that's to maximize the operational space of the robot. And so, yes, good question. This notation is mapping from coordinate system C into coordinate system S. And so let's run through a quick example because, just to make it even more clear what's going on here. So here we have some point P in frame C. And we'll just start with one axis. So here we have 1, 0, 0. And so for us, that point will be up here. And so if we have this point at 1 on our x-axis for frame C, then if I were to just like move the coordinate system of S over on top of this coordinate system for C, we're going to end up with that point over here. Right? So intuitively, we'll know we did this properly if we're getting some value on the z-axis of S. Right? So again, trying to build intuition before we dive straight into the math framework here. So here I have my rotation matrix. Right? And again, I got this by just dot producting my axes from one frame with the axes of the other frame to figure out how much each of these vectors contributes to the other ones. And so this is just the same thing from last slide. Here's our point. In order to go from frame C to frame S, we multiply them together. Importantly, we're left multiplying the rotation. And the only saving, like redeeming factor of this like confusing notation that's probably new to everybody, because it was new to me when I picked up the textbook that uses this, is that we can cancel these things out like fractions. So if you have a C on top here and a C on the bottom here, you can scratch those out and you end up with an S. And this works if you compose multiple rotations together. And so that's one way to think about this, to remember what we're talking about in this concept of transformation. So here, right, I'm just doing basic matrix multiplication. So 0 times 1 is 0. And then so everything's going to be 0 for this top one. Everything's going to be 0 for this middle multiplication. And then finally, I'm going to end up with a value of 1 for z, and that checks out with our intuition over here. So we have a rotation matrix, right? So that rotation matrix is saying, assuming that our origins are the same, then here's how you go from one frame to another, right? From one set of vectors as your basis to a different set of vectors as your basis. What if we want to go back? So here is the rotation from C to S, and then this is the rotation from S to C, right? So we just go backwards. And most of you probably saw this on the homework 0 warm-up, that when asking for the inverse of that matrix question, we gave you some words in the question that suggested that these are rotation matrices. And it turns out to invert a rotation, you only need to take its transpose. And so you can see that these matrices are the same thing, just transposed, right? So rows become columns, columns become rows. It's not just because it's a square matrix. There's a specific condition for particular orthonormal bases that lets you do this transpose inversion thing. Okay, so I can also compose rotations, as I just mentioned a few slides ago. So if I have two rotation matrices, right, to transform from C to B and from B to S, then I can go from C to S by just multiplying these together. And just like I mentioned, so we can look and see like, okay, so this one goes from C to B, and then this one goes from B to S. So I can cross out or cancel essentially these B's here, and I ended up with something from C to S. And so if I just do that multiplication together, I will get my answer from C to S, which we can just visually verify on this slide here. Okay, so doing these rotation matrices is like a bit mind-numbing, and it takes a little while to build an intuition about what's going on here. The most valuable intuition I think that you can have is this projection strategy of figuring out, hey, how much does this vector apply to these other vectors that I'm trying to express this coordinate in? But when we're going to use this, right, we also have to take into account that the origin might not be completely overlapping, as it is in these cases maybe that I'm showing you here. And so if we wanted to express points in a different frame of reference, right, we would normally be able to write this out this way. So what this is saying is that if I have point Q in frame B, and I have a rotation matrix that will transform me from coordinate system B into A, then I'll do that, but I also have to consider the translation, right? So we talked about translation and rotation. So here's my translation, and here's my rotation. And if I add those together, I will get my point Q in coordinate frame A. But we want to make this more concise. And so we introduce this notation called the homogeneous transform. And this is something you'll see a bunch of, which just takes this same equation and puts it into matrix multiplication form. So here we'll have, in this example, a 3x3 rotation matrix. So we're assuming this is a three-dimensional point. So XYZ, let's say. So I have a three-dimensional rotation matrix here. I have my origin of the coordinate system, right, expressed in the destination coordinate system. So this P in frame A goes here. And then the bottom, I need to add a series of zeros and a one just to make the math work out because of the shape requirements for our matrices. And so I get this answer out. So Q in frame A over with an extra element one is equal to this matrix multiplication. So I have my point in frame B, my rotation matrix, my origin of frame B expressed through frame A. And I can just write this out as one thing. The reason why we get this one down here is because we essentially have to add this P of A in. And so we have that little trick of making sure that that happens with this and with this one down here, because these get multiplied together essentially. And so with that, when you get this answer out, you basically just throw away the bottom one here. It's only there to make the matrix multiplication work out, because all we really care about is this Q in frame A. So we want to be able to go from points in some frame B into to have the same thing in points in frame A. So let's look at an example of maybe what a homogeneous transform actually looks like. And this is, again, something that you will be implementing, you will be using multiple times throughout this class. So let's take the two-dimensional case, right? Because that's going to be the one that we deal with our epoch, because we only have to care about X, Y, and then theta, which is the robot's rotation. So here, we're going to have the same concept of rotation and translation, and we're going to have it in homogeneous transform notation. So here's our rotation matrix. So this is a 2D rotation matrix. Here is our translation of X and Y. And here's the point that we have and that we want to express in some other coordinate system. We can also take the inverse of this transform if you wanted to go backwards, but similarly, you can figure this out other ways as well. Do you have any questions about the homogeneous transform before we move onwards from here? Okay, I'll just assume that everybody is as enthralled with this matrix multiplication as I am, but don't worry, once you get this, it's just a tool in your toolbox, and then you can use it to do much more interesting stuff. And just as a quick example of why this stuff is valuable for us, let's take a look at a two-link robot arm on the 2D plane. So here we have our 2D arm, or two joint or two DOF arm. So we have a joint here at the table, or the x-axis. And then we also have a joint up here. These are rotational joints. So we will say that joint 1 rotation is at alpha and joint 2 rotation is at beta. And so for forward kinematics, we want to be able to figure out where is our end effector. And so we have two links, L1 and L2. And then we can just use some fairly straightforward trigonometry to figure out where everything is, right? So X1 and Y1, that's going to be at the end of link 1. And in order to figure out where that is, if assuming we have the length of our link 1, right, which is reasonable, then we just need to know the angle of the joint to figure out where this point is. So we can just do cosine of alpha multiplied by the length of link 1 and sine of alpha times the length of link 1. If I want to find out where this point is, then I'm going to have to use the information right from the previous link to figure that out. So I have to compose those things together. And so here, right, you can see that like we are taking into account the angle alpha and the angle beta. And we can just use this to figure out where our end effector is, right? So for our robot, for a two DOF robot on the XY plane, this is our forward kinematics equation. So I take in alpha and beta, right? Those are my joint angles, and I get out x and y, the Cartesian coordinates of my end effector. Any questions about what forward kinematics means for manipulator arms like this?
I have a quick question. So the inverse kinematics would be to find alpha and beta in this situation?
That's correct. So given an x and a y, figure out alpha and beta.
Awesome, thank you.
And it turns out that is much easier said than done, depending on your robot morphology. And we'll cover that one next time. Okay, so this is forward kinematics for an arm. And usually this is fairly intuitive for folks. It's a pretty straightforward application. But what about for a differential wheel robot like the epoch? So we call the epoch a differential wheel robot because it has two wheels and they're independently actuated. So for our manipulator, the forward kinematics is going to be uniquely defined by the joint angles, right? So given joint angles, there's one answer of where the robot's end effector is going to be. And the measure of the joint angles through the encoders on those motors, so that tells us what angle it's at, is given to us in an absolute sense, right? So it's not like relative to the last measurement. But for a differential wheeled robot, we have something else going on, right? So the measure of our joint angles through the encoders is relative because our wheels are capable of spinning, endlessly. And so in order to figure out where we're at, we have to integrate those values over time, right? We have to take all of those little differences and add them up. So just a quick bit of notational or vocabulary here. When we talk about configuration space, bunch of slides ago, we said for forward kinematics, like Q is that vector of robot joints. So Q is the variable that we use to discuss the robot's configuration space, which is just all of its joint positions. And it's very convenient for us to be able to talk about the robot in terms of a configuration of its motors, because it lets us reduce that to essentially a point, right? Because that's the things that we have control of over the robot, and we can express it as a vector. And so here, we have, for that two-dimensional, for 2 degree of freedom robot from the previous example that we talked about forward kinematics for, we have the first motor and the second motor position as our axes in configuration space. And then this is a graph of Cartesian space, right? So the x and y coordinate, and this one would be in meters. So our motor positions are in radians because it's a rotation. And so if I have a robot that starts fully flat, right? So 0 angle on both of my motors, and we're going to say that angles increase as we go counterclockwise. So at this point of configuration space, everything is 0. So my robot's laying flat. If I go diagonally up to this point here, right? So I'm at pi over 2, pi over 2. So my first angle, right? My first joint is going to rotate to pi over 2, so 90 degrees right here. And then my second joint, beta, is also going to go to 90 degrees. And so I get this formation right here, right? And that's expressed as just a single point in configuration space. And then you can see as we kind of trace this out, so I'll take my beta to pi, right? So it's going to go 180 degrees, and then I'm going to bring alpha back down to 0, and then bring everybody back to 0. And so the robot will do this, kind of like flailing motion that's traced out by these arrows over here before laying flat down at the bottom. So when we talk about configuration space, that is the robot's, in terms of the robot's joint angles. So when we're talking about different types of robots, it's important to talk about holonomic versus non-holonomic systems. And the way that we can figure out if something is holonomic or not is to figure out if closed trajectories in joint space are also closed in Cartesian space. So what does that mean? Well, in this case, I have my motors for my arm, right? And I run it through that sequence of positions and I come back to the starting location. And so my arm goes through a bunch of sequences of stuff and then comes back to the starting location. But if they were wheels, right? If I have my epoch robot and I went through a similar process, right? So now this is my left wheel and this is my right wheel. And I ran it through here, I'm not going to get back to where I started, right? Because you're going to see the robot take some kind of position that looks like this. So as I'm rotating both wheels together, I'm moving forward, and then I do some kind of weird stuff over here, right, with my wheels, and it's just going to spin me sort of close to where I'm at in space. So if something is non-holonomic, that's going to mean that we have to take some extra care to figure out where we are. Again, because our joint angles don't tell the full story of where we're at, right? It's joint angles over time that do that for us. So is this vehicle holonomic or non-holonomic on the 2D plane? So one way to think about that is I rotate the steering wheel 90 degrees, and then I step on the gas for 1 second. Or I step on the accelerator pedal for 1 second, and then I rotate the steering wheel 90 degrees. If I don't end up in the same place for each of those things, then my vehicle is non-holonomic. And so yes, so cars are non-holonomic. Epoch is non-holonomic, which means that we have a bit of added difficulty. So for the last 8 minutes of today, and then for the start of lab here tomorrow, we're going to talk about how to figure out where we are. And that is odometry. So in order to figure out the odometry for our vehicle, we need to be able to model the wheel motion. And we have to turn those wheel motion updates into position updates. And those position updates are found for us through essentially forward kinematics. So odometry is derived from the Greek for measure route. And so what we're going to do is use our sensors to figure out our changes in position over time. And this is useful for pose estimation, which is really the problem that we're trying to solve by creating or by going through this odometry process. And we want to be able to figure out where our robot is so that we know how our motor commands actually impacted where it is in the world. And if we have that, we can make more complicated plans later. Okay, so how do we figure out where epoch is in the world? Well, first thing we need to figure out is what are we able to control? So we got our wheel speeds. So directly, we can control the speed of each of our two wheels. Through that, we can control the direction the robot's at. But for now, it's like just the literal things that we could control is left wheel and right wheel. Okay, so what are we able to actually measure, given that we control each wheel in the rotation of it? So we can control the rotational speed of the wheel. That's true, right? So but basically what we're doing is we're controlling the position of the motor, right? So we can figure out how far a motor has rotated by using an encoder on it. And so that'll just tell us what the joint angle is. It just happens to be that these are continuous joints. So we're able to rotate it continuously. So to figure out where epoch is, we're going to need X, Y, and theta, right? So we need to know the X and Y coordinate for the robot, and we need to know its orientation. So just using, say, forward velocity control on our wheels, how do we measure how far our robot has moved? What do we need to know in order to do that? Thinking back to our, let's say, trigonometry or geometry classes. If I want to find out, so given that I can control how much it's rotating, what do I need to know to figure out how far I've gone, given that I'm using the wheel? Okay, so the diameter of the wheel. So if I have the diameter of the wheel and I know how much I've rotated the wheel, right, I can figure out how much of that wheel has moved on a given surface. Okay, so here's a graphical representation of this, and I can figure out the length of this arc, right? Because this is how far I've moved on the ground with just those two values. And so here we're going to use phi to denote the rotation, right? So the angle that I've rotated is phi in radians, and we're going to use lowercase r to denote the radius of the wheel. And so again, if I note, so lowercase r not changing, or at least in our case, we're going to assume that our wheels don't change over the course of operation. And so phi is something that I get to control, right, from my set position or even like set velocity, let's say. And so we're going to say that the displacement of the wheel, x, is equal to the product of those two things. So the radius multiplied by the change in angle. Whenever we see dots over variables, that means the derivative or the change since the last time step. And so here we can say like the wheel has moved radius times phi, or the change in position of the wheel is radius times the change in angle of the wheel. But we're not just moving one wheel, we're moving a robot that has two wheels on it. And so we want to be able to go from wheel motion to position updates for the robot itself. So here we have a diagram of our robot. So here we have our left wheel, we have our right wheel. We are just going to rotate the right wheel, so that's why this is showing here. D is going to be the diameter of our robot, right? So the distance between both of the wheels. And typically, right, we're going to pick a single point in the middle of the robot to denote the robot's position, right? So the XY coordinate, let's say, of our robot is going to be defined at that one middle spot, which we'll put right here between the wheels. So the x-axis in the robot's perspective is always going to be pointing out the front of the robot. And so I want to know, how far did this just move, right? Given that I've taken my right wheel and I've turned it. So omega is going to be the angle from the left wheel's perspective if I'm moving the right wheel. So we can just draw this diagram and get some familiar looking positions of values, right? So we can compute this arc length because we know the wheel rotation and how wide, or the radius of the wheel. We know this diameter of the robot because that's not changing. We have the robot, we can just measure that. And we might not know this directly, but we can certainly compute it. So in this case, right, we know that this arc length is equal to these two things multiplied together, right? Because that's the same thing we just did on the previous slide to figure out, well, what this arc length is. So I can set those things equal to each other. Right, so the angle multiplied by the radius is going to be the same thing as the arc length, right, which I already have from a different calculation. And so I can just solve for omega r by dividing the robot diameter over to the other side. So now I know how much the right side of my robot has rotated, right, with respect to the left side. But what does that actually do for me? Well, I want to be able to figure out, right, where my robot has actually moved. Okay. So what happens if both wheels are moving, but maybe they're moving at different speeds? I can leverage something about this robot being a rigid body, right? I see that the point between my wheels, it's always going to be in the middle of the two wheels, right? So the position here that I'm using as the reference point for my robot is going to be the average position of the wheels at any given time, right? Because I know that because it's in the middle of them. And so the displacement of the middle of my robot is just going to be the average displacement of my left and right wheel. So my right wheel is going to move by the radius of itself multiplied by how much it's rotated. The left wheel is going to move by the same thing, but rotate for the left wheel. And the average of those two things is going to be where the middle is. And that's where my robot is. So if we go back to the case where only one wheel is moving, then where does the center of my robot go? Well, one of these values, let's say the right wheel is turning. So phi.L is going to be 0 because the left wheel is not rotating. And so that's just going to reduce this then to x.r is equal to whatever movement the right wheel is taking divided by 2. Okay, so these are the building blocks that we'll need to figure out where our robot is actually updating over time, because we're going to want to be doing this every time step, right? So we're going to have our wheels rotate a certain amount every time step, and that's going to cause some amount of displacement in our robot every time step, and we're going to want to sum that up. And so in tomorrow's lab, it's going to be a 2-week lab. We will start implementing odometry. We're going to have a robot essentially follow a closed course. So we'll have instructions for you to get your robot to do that. And as the robot moves around this course, you're going to plot its location. And we're going to start talking about some of the sources of error for that, where this could go wrong, and then things that we can do to make our robot's estimation of its position more accurate. And with that, we are at time, so I will stop lecture. If you have any questions, feel free to throw them in chat, and I will stick around and answer them to the best of my ability.